Date: July 13, 2020. Author: Ninit Gajanan Naik. As complexity of the automotive embedded systems grew, there was a rising demand for an open industry standardized software architecture for development of automotive electronic control units. In a bid to address this concern, a partnership between world leaders in automotive domains ensued, which resulted in the formation of AUTOSAR, which stands for Automotive Open Systems Architecture. Figure 1. AUTOSAR Layered Architecture. AUTOSAR Layered Architecture. AUTOSAR architecture consists of 3 layers as seen in Figure 1. Let us see about each layer in brief. Basic software layer. This is the bottommost layer in the AUTOSAR architecture and directly interacts with the underlying hardware module and provides hardware abstraction for the upper layers. This layer provides standardized architecture in order to implement memory stack, diagnostics services, operation system and communication stack, which we will see further. Runtime environment layer. RTE acts as a common interface between application layer and BSW layer to provide means of interaction between them. It facilitates information exchange between application software components and basic software and applications. Application layer. This is the final layer of AUTOSAR architecture and contains application software components, SWC. These are completely hardware independent. AUTOSAR communication, COM, stack. Figure 2. Components of AUTOSAR layers. As seen in Figure 2, COM stack or communication stack of AUTOSAR consists of communication services, communication hardware abstraction and communication driver present in the BSW layer. Moving further, let us see different components present in each layer of COM stack. Figure 3. Components of AUTOSAR COM stack. COM. AUTOSAR COM is a service layer module lying in between RTE and the Pdu router. It is used to transfer signals to and from the RTE layer. It packs the signals to a PDU at the transmitter and unpacks received PDU to provide signal level access to the application at the receiver. Thus, signal level or PDU level communication is possible irrespective of the underlying protocol. In this module we also configure the cycle time, offset, repetition period, for event frame at PDU level. It is also used for grouping of PDUs. Pdu Router. The job of a Pdu router is to provide routing paths to the IPDUs within the communication stack. It routes the receiving IPDUs to the upper COM module or to diagnostic services or the error detection module. For transmitting, it routes the IPDUs to the respective bus interface. For example, it receives a PDU from the AUTOSAR COM module and then routes it to CANIF module for transmission through CAN bus, LINIF module for transmission through LIN bus. AUTOSAR TP. Here TP stands for Transport Protocol. This module is bus specific and its configuration depends on the underlying bus protocol. It can be CAN bus protocol, LIN bus protocol or any other communication protocol. This module facilitates segmentation of messages at transmission along with flow control and reassembling of segmented messages at reception. Bus State Manager. The Bus State Manager module is responsible for the control flow of the respective bus. It also handles startup and shutdown features of COM transmission and monitors signal timeouts. It interacts with the communication hardware abstraction layer and system services layer. It can either have CAN State Manager, CANSM, LIN State Manager, LINSM based and the bus protocol. Bus Transceiver Driver, internal US driver. It is a part of the AQ abstraction layer. It can either have CAN-TRCB for CAN transceiver, F-TRCB for Ethernet transceiver, FRT-RCB for FlexRate transceiver, etc. This module provides hardware-independent interface of the underlying bus transceivers to the upper layers of communication stack. It provides services for initiating transmissions and callback functions for notifying receive events, independent from controller hardware. External Bus Driver. This module is a part of the AUTOSAR MCAL layer, X, CAN drive, LIN drive, FRDRB. It actually interacts with the underlying hardware of the AQ and provides a hardware-independent interface to its upper layer. This module is hardware dependent and the driver codes may vary according to the underlying hardware. BUSIF is the only module that can access this bus driver. What is CAN bus protocol? CAN stands for Controller Area Network. It is called CAN bus protocol because it is implemented as a logical bus topology. It is widely used in automotive electronics. Prior to the introduction of the CAN bus, each AQ had to be connected to one another to enable communication between them, resulting in a large mesh of wires. However, now each AQ has to be connected just to a single bus, thus reducing the wire length as well as overall connection complexity in an automotive system. Thus, the CAN bus protocol allows AQs to communicate with each other without any complex dedicated wiring in between. The reason for choosing CAN bus implementation in order to study COM configuration is that it is very widely used in automotive electronics these days owing to its following features. Highly robust to electronic disturbances and electromagnetic interferences, which is ideal in vehicular environment. Less prone to errors as well as more efficient. CAN protocol is flexible. Each CAN connected AQ can receive all transmitted messages. It decides relevance and acts accordingly. Thus addition or removal of AQ on the bus is easy. Based on 2 wires, CAN high and CAN low, which reduces installation hassle. More importantly, it is a low-cost interface. Figure 4. Example of CAN bus in an automotive vehicle. COM configuration for CAN bus implementation. Figure. AUTOSAR communication stack for CAN bus protocol. Now we will discuss the AUTOSAR communication stack with respective CAN bus protocol. Communication P stack with respect to CAN protocol consists of AUTOSAR COM module, Pdu Router, CAN state manage CANSIM, and CAN transport protocol CANTP, from service layer, CAN interface CANIF, CAN transceiver driver from AQ abstraction layer, and CAN driver from MCAL layer. AUTOSAR COM and PDUR modules are generic and function irrespective of the underlying communication protocol. We will further study each module involved in setting up CAN communication stack and all the import configuration parameters associated with each of them. COM. The underlying purpose of providing COM configurations is to establish a communication of the system between the upper RTE layer and the below PDU router irrespective of communication protocol. This is done by defining and configuring 4 different objects, viz. IPDUs. IPDU contains a message received from a certain module or a message that needs to be transmitted to a certain module in the communication stack. IPDU groups. If we have a large number of IPDUs, then we can group them in different groups. Signals. A IPDU can consist of 1 or more signals. Signal groups. Signals can be further formed into signal groups if several signals need to be sent to the same IPDU. COM module contains 2 main containers, COM_general and COM_config. COM_general multiplicity 1. It is used to provide various general configuration parameters for the COM module. Following are some important parameters of COM_general container. COM configuration used it. If this Boolean parameter is set to on, then any error shall lead to call to API function det_report error, multiplicity 0.1. COM cancellation support. It is a Boolean parameter which is used to disable cancellation features used for cancellation of PDU transmit requests. Multiplicity 0.1. Commendable signal group array. It is a Boolean parameter used to deactivate the signal group array access API. Multiplicity 1. COM supported Ipdu Groups. It is an integer parameter which tells the maximum number of supported IPDU groups. Multiplicity 1. COM version info B. Boolean parameter to deactivate the version information API, COM_get version info. Multiplicity 1. COM retry failed transmit requests. If this parameter is set to true, retry of failed transmission requests is enabled. Multiplicity 0.1. Commendable DD for cyclic transmission. If this is enabled, then it provides a minimum delay time monitoring between cyclic and repeated transmission of IPDUs. Multiplicity 0.1. COM_config multiplicity 0.1. It contains the 4 major containers: COM signals, Ipdu groups, and COM signal groups. It also has configuration parameters for transmission mode configuration, signal gateway configuration, time-based configuration, and filter parameter configuration. Ipdu multiplicity 1. This container is used to provide definition to different IPDU parameter without which no communication via the COM module is possible. The Ipdu is also linked to PDU via the Pdu. IPDUs contain 1 or more signals and/or signal groups. Following are some basic properties of Ipdu. Ipdu handled. This is a numerical value assigned as the ID for this IPDU. This ID is used to refer to this IPDU in various transmitting and receiving API calls as well as respective callback APIs. Multiplicity 0.1. Pdu. It provides reference to the global PDU structure of the COM stack. Multiplicity 1. Ipdu Group brief. It refers to the IPDU group to which this IPDU belongs to. Multiplicity 0 asterisk. Ipdu signal ref. This provides references to all the signals that are included in this IPDU. A IPDU can contain 1 or more individual signals. Multiplicity 0 asterisk. Ipdu signal group brief. This provides references to all the signal groups that are included in this IPDU. A IPDU can signal groups where several signals need to be associated with the same IPDU. Multiplicity 0 asterisk. COM-UPDU callout. This parameter defines the existence and the name of a callout function for the corresponding IPDU that is called upon on receival of the IPDU or before transmission of the IPDU BUPDUR. Multiplicity 0.1. COM-UPDU direction. The direction defines if this IPDU, and therefore its contributing signals and signal groups, are to be transmitted, sent, or received. Multiplicity 1. COM-UPDU signal processing. It is used to configure when the signal indication takes place, either in immediate mode or in deferred mode. Multiplicity 1. If the COM-UPDU direction is set as send, we need to set additional parameters like whether the transmission is cyclic or periodic, etc. This is added by adding a COM-TextUpDu object. COM-UPDU group multiplicity 1. It contains the configuration parameters of the COM module's IPDU groups. If there is no COM-UPDU group container included, then no IPDU group is defined. In this case, no communication via the COM module is possible. Multiplicity 1. COM-UPDU group ANDLEAD. The numerical value used is the ID of this IPDU group. It is required by the API calls to start and stop IPDU groups. Multiplicity 1. COM-UPDU group brief. It provides references to all IPDU groups that include this IPDU group. Multiplicity 0 asterisk. COM signal. An IPDU can be formed of one or more than one signals. These signals coming from the different applications from the RTE layer are packed into a PDU before being transmitted to the Pdu router. This container provides various parameters to configure the signal bit position in the PDU, signal bit size and other properties. COM handleAD. This is a numerical value assigned as an ID to each signal. It is required by different API calls pertaining to operation on signals. Multiplicity 0.1. COM timeout factor. It defines the timeout period for the deadline monitoring. Multiplicity 0.1. COM transfer property. Following options define if this signal can trigger the transmission of the corresponding IPDU. Multiplicity 0.1. We can set one among these 5 options. Triggered, pending, triggered underscore on underscore change, triggered underscore without underscore repetition, triggered underscore on underscore change underscore without underscore repetition. COM bit position. It states the starting position of the signal in the IPDU. It will be a multiple of COM signal type. Multiplicity 1. COM bit size. It defines the size of signal in bits. Multiplicity 0.1. COM signal endianness. Defines the endianness of the signal's network representation. It can be big underscore endian, little underscore endian, opaque. Multiplicity 0.1. COM signal initialu. It is used to set initial value or default value of signals in varied cases. Multiplicity 0.1. COM signal length. It specifies the n in bytes 1.8 of the type UINT8N. For other types it will be ignored. Multiplicity 0.1. COM signal type. It specifies the type of signal conforming to one of the different AUTOSAR types like Boolean, SINT8, UINT8. Multiplicity 1. Commodification. If reference is the callback function that needs to be called on either the sender or receiver side. Multiplicity 0.1. COM notification. Only valid on the sender side. Defines the name of the callback function to be called on the error message. If this parameter is omitted, no error notification shall take place. Multiplicity 0.1. COM timeout notification. Defines the name of function to be called on the sender or the receiver side if timeout occurs. Multiplicity 0.1. COM signal group. When we need to send or receive several signals to the same Ipdu, then these signals can be clubbed together to form a signal group. Note: this container includes different parameters with names similar to COM signal container and act exactly the same only on a signal group rather than individual signals. Therefore, in this section I will only mention the parameter names. To understand their behavior, please refer to the COM signal section. COM handleAD multiplicity 0.1. COM timeout factor multiplicity 0.1. COM first timeout factor multiplicity 0.1. COM transfer property multiplicity 0.1. COM notification multiplicity 0.1. COM invalid notification multiplicity 0.1. COM error notification multiplicity 0.1. COM timeout notification multiplicity 0.1. Pdu Router PDUR.